So far, we've used the difference quotient to take the derivative of various functions. But as you can imagine, having to use the difference quotient for the derivative every time we need the rate of change could be very time-consuming and bothersome. So what we're going to do in this section is derive some of the more used formulas, and in the next few sections after this, we'll expand on the ones we're going to look at in this section. But before we go ahead and take the derivative of a power function, I want to start with some review of binomial expansion. So hopefully at some point in your previous courses you have expanded binomials. Usually we start with taking a plus b squared, or a plus b times a plus b, and distribute the two parentheses and combine the like terms. You get a squared plus 2ab plus b squared. And if we do the same thing for a plus b cubed and write a plus b 3 times and multiply and distribute, we end up with a cubed plus 3a squared b plus 3ab squared plus b cubed. And then if we go ahead and take this to one more power, to the fourth power, we'll end up with a plus b to the fourth equaling a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. A few things here to notice. Our very first term in this polynomial would be the first term of the binomial with the same exponent as the binomial, right? So if you're taking something to the fourth power, I am going to have the first term, in this case a, to the fourth, and the very last term of the polynomial we end up with is the second term of a binomial to the same power. And in between, what happens is the exponents for a keeps getting smaller while the exponents for b keeps getting bigger. So I'll start with a to the fourth here, then a cubed, then a squared, then a, and then finally to a to the 0, right? A to the 0 is 1, so this is 1b to the fourth. And the b's would go the opposite, right? So b to the fourth, b cubed, b squared, b, and b to the 0, or 1. So that leaves us with the coefficients that we have. Notice the first term and the last term have just coefficient of 1. The middle terms do have coefficients. The coefficients of the second term always matches the exponent for the binomial, right? So if I have taken to the fourth power, this coefficient of the second term would be 4. And the same is true if I go the other way. The second term from the end would have the same coefficient of 4. And then there will be other terms with other coefficients, so we'll address those in a second. So in general, what we have as a general formula for binomial expansion is that if we take a plus b to the n, we start with a to the n. The next term would have n as the coefficient. The power of a gets 1 smaller, and then I gain a b. And then the power of a gets 2 smaller, b squared. And then there will be some coefficient, nc2 or n choose 2 is defined to be the factorial of n. So n factorial over r factorial n minus r factorial. So this one would have been, in our case up here, for example, 4 factorial on the top because our exponent is 4. And the term that I have here on the bottom would have a 2 factorial and then 4 minus 2 factorial. That would give us 6. But what we really want to focus on is the pattern that we have here, because that's what we're going to need to derive the formula for a power function, right? So next we're going to look at that derivative. So we'll start with assuming that we're taking x to a positive integer. So we'll plug everything into our difference quotient formula for the function x to the n. So we'll have x plus h to the n, that's f of x plus h, minus f of x, which is x to the n over h. And apply the binomial expansion we just saw 2x plus h to the nth power. So this is what we get. So starting with x to the n, and as we said, the next term would be n x to the n minus 1 times h, and this pattern holds all the way to h to the n, and then we have the minus x to the n that was at the end. And as you notice, in the numerator, the x to the n that I have in front and the x to the n that I have at the end cancel, and we'll end up with this new fraction where every term in the numerator now has an h. So the two terms that did not have an h canceled each other. That allows me to factor an h out of all of them. And as a result, the very first term is just going to be nx to the n minus 1. The h is taken out. And all the other terms that we had in the polynomial have an h that now has an exponent that's 1 smaller than it used to be, right? So if we had an h squared, we took an h out, now it's h to the first. H cubed is now h squared, and so on. And finally, the h to the n at the end is now h to the n minus 1, right? So we took an h out of all of them, and that allows me to cancel the h that is taken out with the h that's in the denominator, and have a polynomial now that has no denominator. And we can go ahead and now find the limit as h goes to 0. And notice that the first term has no h in it, so h going to 0 doesn't affect it. All the other terms have an h. So as h goes to 0, what we're going to end up with is these terms all have 0 to a power, and the first one doesn't. So what we're left with at the end is just the term nx to the n minus 1. Right? So far that means if we have a power function x to a positive power, and that power is an integer, we can prove using binomial expansion that the derivative is n times x to the n minus 1, where n is the exponent we started with. So if I have an x to the 5th, I'm going to get 5 times x to the 4th. Now, later on, we're actually going to verify that this holds for other powers too. So the power doesn't necessarily have to be an integer, a positive integer. It works for any real number that I have as my exponent, and would also work for negative powers. So generally, the derivative of x to the nth is going to be nx to the n minus 1, right? And that also can be generalized to some other formulas we had already established by looking at the slope of a tangent line. So we know that the derivative of x is just 1. Because x is a straight line and its slope is always 1. So the derivative would always be 1. But it is consistent now with the formula that we have verified. So if I start with x to the first power, the derivative would be 1 x to the 0 power. So that's 1 times 1, or 1. And also we can use that to verify another fact we had seen before. The derivative of a constant function is 0, right? So graphically, if my function's just constant, I have a horizontal line, right? So if f of x is 7, I have a horizontal line that's 7, and the derivative of that would be 0. The slope would be 0. But once again, we can just kind of derive that from this result. You can think of that as starting with an x to the 0 power. Okay. So if I then continue to our next fact, we're going to look at other derivatives that we can now come up with using the ones we've seen. Right. So look at some derivatives from the old ones. So start with the derivative of a constant times a function, right? So whatever f of x is, if it's multiplied by a constant, we want to be able to take that derivative and see how the constant affects it. So using the difference quotient again, I'm going to have a c times f of x plus h minus c times f of x over h. We can factor the c out of the numerator. And again, as h goes to 0, since c is a constant and has no value, no h in it, we can take that constant, move it to the front using some of our limit properties we had seen. And then what I'm left with here now is a c multiplied by this difference quotient. And that difference quotient is the definition of the derivative of f of x. So I end up with c times f prime of x. So that means that if a constant is multiplied by a function, its derivative would be the constant multiplied by the derivative of a function. Now, this only applies to a constant product with a function. We'll later on show how it would work if I'm multiplying a function times another function. Okay, so here's some other formulas. We can generalize using our limit definitions. A similar derivation could apply to them. So the first one says if I'm taking a derivative of two functions added, as long as they're both differentiable, I can take the derivative of them separately and add the result. And the same is true if they are subtracted. Okay, not true if they are multiplied or divided. Right, so only in case of addition and subtraction, I can apply the derivative separately, once again, as long as my functions are differentiable to start with. Okay, so next we are going to look at another common function and derive its derivative. We're going to look at derivative of exponential functions. Right, so an exponential function being f of x equals e to the x, where if you recall, e is just a constant, right? It's roughly 2.71828. So notice again the difference between an exponential function and a power function. So in a power function, the base was the variable, while the power or the exponent was a constant. In an exponential function, the base is a constant, while the power is a variable. So we want to know how to take a derivative of a function like that. And again, we'll start with just e to the x, because we had looked at some properties of e to the x in the previous sections when we talked about the limits of it. And in the future section, we will generalize it to other constants taken to the x. Right? So to come up with what we need to derive the formula, first thing we're going to look at is at the f prime of 0 in this case. That's going to come in handy when we're using our derivation. So let's figure out what f prime of 0 is if f of x is e to the x. Right? So f prime of 0, based on the difference quotient, will be e to the 0 plus h minus e to the 0 over h. E to the 0 plus h is just e to the h. E to the 0 is 1. And on the bottom, I have an h. And that is one of the limits we had seen when we were looking at our limits in the previous sections. In our video about limits, we looked at that particular limit by examining its graph. So the green function in this graph is e to the x. The blue line is the tangent to it. So if we zoom in and take a look, we are interested in the f prime of 0, which would mean the slope of a tangent at 0. So we need the slope of this blue line. And it should be easy enough to see that the slope of this blue line is 1. So if the rise is 1, the run is 1. So I get 1 over 1, which is 1. So this limit, e to the h minus 1 over h, is going to equal to just 1. And again, that's a fact I'm going to need to use shortly, right? So now we're ready to take the derivative of e to the x. Right? So applying the difference quotient now from scratch with no value for x, we have e to the x plus h minus e to the x over h. We'll notice here I have something where the powers are added. That means I can break this up into 2 parts, e to the x multiplied by e to the h using the exponent rules, right? So if 2 things are multiplied, their exponents would have been added. So then what we'll do is factor e to the x from the 2 terms on the top. And then try to take the limit as h goes to 0. Once again, e to the x has no h in it. It can be taken out of that limit and put in front. So I have e to the x multiplied by the limit as h goes to 0 of e to the h minus 1 over h. And this limit we just looked at to be equal to 1. Right? So this is e to the x times 1. Or e to the x. So the derivative of e to the x remains e to the x. Okay, and again, that's going to be a common function we are going to be working with throughout the semester. Exponential functions come up quite often in life science applications. Okay, so that adds one more basic function to the list of functions we can take a derivative of. Next, we would like to consider some trig functions. And before we go ahead and take the derivatives, again, a quick review of some trig function properties. The first one that we are going to need in our derivation is the formula for the sine of a sum. Right, so if you recall from trigonometry, if I'm taking sine of a plus b, the formula would require me to take the sine of a multiplied by cosine of b and add the result to sine of b multiplied by cosine of a. Right, just a refresher of the formula for sine of a sum. Next, we're going to look at some limits we had seen in the previous sections. First one being sine of x over x as x goes to 0. So that limit we'd seen to be equal to 1. If you recall, this is the graph that we have for sine of x over x. And as x gets closer to 0, our function is getting closer and closer to 1. And its counterpart that we are going to need is limit as x goes to 0 of cosine of x minus 1 over x is equal to 0. Again, if we look at the graph for that function, we'll see that that function gets closer and closer to 0 as x gets close to 0. So those we're going to need in our derivation for derivative of sine of a function. So, or sine of x. So we're going to start with the derivative of sine of x. Apply the difference quotient definition of the derivative to it. Limit as h goes to 0 of sine of x plus h minus sine of x over h. We'll apply the sine of a sum formula to the first part of that numerator. That gives me sine of x cosine of h plus sine of h cosine of x minus sine of x all over h. So the terms that I have on the top, 2 of them have a sine of x in it. So what we'll do is factor a sine of x out of those 2 terms. So this first term and the last term we've taken a sine of x out of. That leaves us with a cosine of h from the first term and a minus 1 from the second term. Right? So there's here, and this sine of h cosine of x term remains the same. So now as we take the limit as h goes to 0, I can break this up into 2 limits. And then some of these pieces don't have h in them, right? So our limit is as h goes to 0. So we can rewrite this is a limit as h goes to 0 of this first part over h, plus limit as h goes to 0 of the second term in the numerator over h. Take out the pieces that don't have an h in them out of the limits, and the limits that I am left with now are the limits we just looked at a few seconds ago. Limit as h goes to 0 of cosine of h minus 1 over h we saw is equal to 0, and limit as h goes to 0 of sine of h over h was 1. So we have sine of x times 0 plus cosine of x times 1, which just gives us cosine of x. So the derivative of sine of x can be shown to equal to cosine of x. So that's our basic formula for the derivative of sine of x. And then we can do something similar to derive the derivative for cosine of x. Apply the formula for cosine of x plus h. That formula is cosine of x cosine of h minus sine of x sine of h. So when we do the same process, you end up with an extra negative in there, and the derivative of cosine of x is going to end up being negative sine of x, right? So just to sum it up, these are the formulas we have seen in this section. Derivative of x to the n is nx to the n minus 1. Derivative of x is just 1. Derivative of constant is 0. Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. And derivative of e to the x remains e to the x.